Okay, hello everyone. I'm Seong Cha and I'm an assistant professor in the Department of Software. So in this video, I will focus on introducing software testing, especially white box testing. So first of all, I will motivate you why we need software testing. Then I will introduce the white box testing, namely symbolic executions. Okay, I will start with the need of the software testing. First, there is no doubt that software is everywhere nowadays. So let me ask something. So how many software are there in the world in today? 10 million or 100 million or 10 billion? Imagine your answer in your mind. The answer is, I don't know either. I was wondering about the number of software, but I couldn't find any statistics about that numbers. Instead, I found the number of software development in the world. From this article, the number of software developers in 2019 was about 24 million. Then that number will rise to 28 million by 2024, and 4 million by 2030. Also, the size of the software is increasing rapidly. For example, the number of lines for the Facebook, including backend, is about 62 million lines. And the number of code line for the modern high-end car is about 100 million lines. More surprisingly, the number of code lines for Google, including all internet services, is 2 billion lines. And in addition, software complexity is usually exponential in the size of software. So that is, currently, software is everywhere nowadays, and its size and complexity are rapidly increasing now. And unfortunately, software bugs are also everywhere. I brought some infamous software failure cases. The Ariane Rocket 5 explosion is one of the worst software bugs in history. The European Space Agency developed the Ariane rocket for about 10 years and paid $7 billion. But because of a very tiny bug, this very, very expensive rocket exploded 37 seconds after the launches. This failure was caused by a data conversion from the 68-bit floating point to value 16-bit integer value, thereby introducing integer overflow. So if you are interested, click this YouTube link and I attached, and watch the explosion of the Ariane Rocket 5. And another famous case for the software failure is the Dirac-25, which is the radiation therapy machine produced by Atomic Energy of the Canada Limited in the 1982. And because of the race conditions in the Dirac-25, this machine sometimes gave the patient radiation doses that were hundreds of the times greater than the normal. As a result, the machine, Dirac-25, actually killed at least 6 patients. Okay, so back to the first question. So why do we need software testing? This is because we do not want to lose our money or our time or our life. So we need software testing for finding such serious bugs in the early stage of the software development process. So I think you are all motivated now for the need of the software testing. So at a high level, software testing can be seen as automatic test case generation techniques. So this technique takes a target program as an input, and it aims to generate the test cases that are likely to trigger the program bugs. But when testing in real-world programs, software testing technique can hardly know where software bugs are because of the large size of the software and its high complexity. So I brought the most famous scene in the movie Taken. I don't know where the bug is, but I find it and I kill you. So anyway, instead of finding software bugs directly, software testing usually aims to increase code coverages. Intuitively, a code coverage indicates how many codes are executed by the generated test cases. For example, in this picture, the green lines denote the executed line and the red one denotes the line that are not executed yet. And so the goal of the software testing is to increase the number of executed code lines like green lines. So the hypothesis for increasing code coverage in software testing is that the more code we executed in a target program, the more bugs we can find. For example, suppose that you should drive one of the 2 self-driving cars. The software equipped in the first car only executed 10% of the entire software code. And the software of the second car executed more than 90% of the code. So will you drive the first car or the second car? Definitely we will choose the second car. Okay, from this slide, I will introduce some representative code coverage metrics, including line coverage and branch coverage and path coverages. First, the line coverage is simply calculated by counting the number of executed lines until now. From this toy code on the left, total lines is 6, and we can achieve 100 lines covered by executing just 2 test cases. First, let's execute the test case, which is x is 19 and y is 10, y is 0. Then we can cover the 5 lines highlighted in yellow. Then the line coverage will be more than 80%. And second, we executed another test case that is x is 0 and y is 25. And then we can reach the 100 line coverages. Well, the branch coverage can be seen as a more fine-grained metric than the line coverages. A branch coverage is also calculated as counting the number of exercise branches. And as we all know that the number of branches in the program is twice the number of the if or while statement. So in this example, the number of branches are 4, and the branch coverage also can reach 100% by executing only 2 test cases. When executing the first test case, which is x is 90 and y is 0, we can cover the 2 branches, which are the first true branches and the second first branches, highlighted in green. Highlighted in blue. And then the remaining 2 branches are also covered by running another test case, which is x is 0 and y is 25. Lastly, the path coverage is more fine-grained than the branch coverages. And usually the number of execution paths is exponential in the number of branches in the programs. So in this code, the number of execution paths will be 2 to the 2, so 4. And to reach the 100 path coverages, we require at least 4 test cases. The first test case will cover on execution passing these 2 first branches. And the second test case will cover another execution path, which is cover the first branch and the second 2 branches. Third one is also reach another path. And the last one cover the path executing the two branches. That is, in general, achieving full path coverage is much harder than achieving full branch coverages. But full path coverage is more likely to discover the bugs than the full branch coverages. From this slide, I will explain the software testing method for achieving high code coverages. At a high level, we can classify software testing method into black box and the white box testing. The key difference between them is whether using the source code during the testing. Black box testing, for example, takes only a binary file, which is not source code, as input, and execute the program without observing or using the source code to achieve high code coverages. And on the other hand, white box testing takes source code as input and decide which test cases to generate systematically by using the source code. Today, we will learn a specific white box testing method, which is symbolic execution. This technique is expensive, but very systematic approaches. More specifically, symbolic execution is the promising software testing widely used in both academia and industry. The key idea of symbolic execution is to replace program input with the symbolic variable and to execute the program with this symbolic variable. I will explain how to work symbolic execution from the laters. And these are symbolic execution tools used in the industry or academia. And for your interest, the last 2 ones, which is Chameleon and Homie, are mine. This is my tool. Anyway, the symbolic execution tool, for example, says successfully found 1/3 of all the bugs discovered during the development of the Windows 7. And finding this bug, of course, saved Microsoft millions of dollars, actually. And another symbolic execution tool, which is Java Pathfinder, successfully found a serious bug in the NASA flight softwares. That is, this symbolic execution is actually a powerful technique for finding real-world bugs. And in particular, a modern symbolic execution is called the dynamic symbolic execution. And there are 2 major flavors of the dynamic symbolic execution, which is concurrent testing and execution generated testing. And concurrent testing is first introduced by Kaushik Sen, a professor at UC Berkeley, and EGT is presented by Christian Cutter, a professor at Imperial College London. These 2 techniques are all dynamic symbolic execution because of the combination of the concrete execution and symbolic execution. But more specifically, their working process is slightly different. First of all, I will explain how a major approach of the dynamic symbolic execution, which is concurrent testing, works. As you can see, this terminology concrete is mixing the terms concrete and symbolic, like the term brunches, which is combination of breakfast and lunch. First, I will explain the limitation of the pure random testing using this about 10 lines simple code. So this is a very simple quiz. So when the range of the x and y values is 1 to 100, what is the probability of reaching the error branches when we using random testing? Anyone guess the answers? 0.4% or 0.4% or just 4% or 40%? The answer is 0.4%, even though the code is very simple, having and has only 10 lines, and the integer range of the x and y even highly restricted from 1 to 100. But if we use the concurrent testing, we can search error triggering input in just 3 runs. So I will explain how to generate such input by concurrent testing step by step. First of all, concurrent testing maintains 3 components: concrete state and symbolic state and the past conditions. And concrete state is a mapping from the program variable to the actual values. And the symbolic state is a mapping from the program variable to the symbolic values. And the past condition represent the sequence of the branch conditions taken during the program execution. So in this code, suppose that the initial random input are x is 22 and y is 7. So in concrete state, x will be 22 and y will be 7. And in symbolic state, x and y are symbolic values are alpha and beta. And at the first line, we do not meet any branch yet, so the past condition is just true. Okay, let's execute the program with this random input. At the next line, because of these twice functions, the value of z will be 14 in concrete state and 2 times beta in symbolic state. And past condition is still true because we do not meet any branches yet. And the next line at these branches, z value is not equal to x, as you can see in the concrete state. So we go to the else branches. And because we encounter of branches, we will update the past condition by adding the else branch condition, which is z is not equal to x. So when we update the past condition, we will use the symbolic values. So in past conditions, 2 times beta is not equal to alpha will be updated in the past conditions. And then the first iteration is ends, and because we reach the end of the programs. Then in order to go into the true branches at the next program execution, we negate the past conditions. So when we use the SMT solver to find alpha and beta values, which satisfies the negated past condition, which is 2 times beta is equal to alpha. In this case, the SMT solver easily finds satisfiable inputs such as alpha is 2 and beta is 10. In this case, this equation 2 times beta is equal to alpha is true. So at the second program execution, we start with this new generated input, which is x is 2 and y is 1. At the next line, z will be 2 in the concurrent state and 2 times of beta in the symbolic state. And at the next line, we can get into the true branches because x and y's are equal in the concrete state. And we update the true branch condition, which is 2 times beta is equal to alpha in the past conditions. At the next line, x is not bigger than y plus 10. So we go to the else branches. Because we encounter another branches, we add the first inner branch condition, which is alpha is less than equal to beta plus 10. Then the second iteration is ends, and in order to get into inner true branches in this time, we negate the second branch condition, which is the highlighted in red. That is, we call SMT solver again and find some inputs which satisfies the formula 2 times beta equals alpha, and also alpha is bigger than beta plus 10. And SMT solver can find the satisfiable solutions, which is input like alpha is 22 and beta is 11. In this case, this equation is 2 times beta equal to alpha, and alpha is also bigger than beta plus 10. So at the third iteration, we start with this new input x is 22 and y is 11. And that will be 22 and 2 times beta in symbolic state. Next time we get into inner branch condition and we update the true branch condition in the past condition. And finally, we get into inner true branch, which is the triggering error. That is, we succeed in finding this error triggering input. And as you can see, concurrent testing is a quite systematic and effective method comparing to the random testing. I will try to make this example code a little bit more difficult to code like the code highlighted in yellow. Now the twice function is a square function on each input. Let's execute this modified program symbolically again. Next line, z will be 49 in concrete state, and the square of beta, z is square of beta in symbolic state. Next line, at these branches, z value is not equal to x value, so we go to the else branches, and we will update the past condition by adding this else branch condition, which is the square of beta is not equal to alpha, will be updated in the past condition. And then the first iteration is end, because we reach the end point of the program. And in order to go into the true branch at the next program execution, we negate the past condition again. So we try to find some alpha and beta values, which satisfies this negated past condition. The square of beta is equal to alpha. And here is the problems. Suppose that this SMT solver does not support the non-linear constraint like the square of beta, then we can't find a solution from these solvers. So of course, in real world, there exists some SMT solver supporting non-linear constraint. In this case, when the solution can't be found by SMT solver, concurrent testing simplify the non-linear constraint by replacing some symbolic value with concrete values. So in this case, we substitute the symbolic value beta into the value of y in concrete state, which is 7. So then the simplified constraint is just 49 is equal to alpha, can be easily solved by SM solver. Then the next input x is 49 and y is 7 will exercise through branch in this code. In this way, concurrent testing systematically generate the test cases. Okay, let's summarize the first lecture of Whitebox testings. First, we learn the general goals of software testing, which is finds many bugs and maximize code coverages effectively. Second, we learn a major Whitebox testing method, which is concurrent testing, how it works. And in the next class, we will cover the remaining part of the Whitebox testing, such as execution general testing or open challenges in symbolic execution, and the diverse research topic related to these Whitebox testings. Okay, this is the end of this lecture, so see you next week. Goodbye, everyone.